Hi everyone. Thanks for attending this lecture. I'm Lin. Today I'm going to talk about the joint work with my supervisor Boston, an iterative approach to improving solution quality for AC optimal power flow problems. I'll start from the mathematical formulation of AC optimal power flow. It is an optimization problem that minimizes the total generation cost subject to a set of physical constraints and the supply-demand balance constraint. Particularly, this balance constraint is nonlinear, so its OPF is a non-convex problem. A challenge in solving SOPF is the existence of multiple solutions, and a nonlinear programming solver like IPOpt, it may terminate at some suboptimal solution and stop looking for a better solution. So to illustrate the existence of multiple solutions in SOPF, I will use a two-bus network as an example. And in this example, I will fix the voltage magnitudes and only optimize the phase angles, and also ignore the reactive power to simplify the situation. So for this two-bus network, we can write out its SOPF formulation. It's a constant problem. And in the nonlinear programming solver, they actually uses barrier method to solve a sequence of unconstant problems. So we can transform this SOPF problem into its panelized version. And we can use the panelized problem to study the solutions of SOPF. For this example, if we plot the function values of this panelized problem, we can say there are two solutions. If the nonlinear programming solver reaches the strictly local solution, it will terminate at this point and won't keep looking for a better solution. So our question is there any method, is there any way to get the solver out of this trap and to find the globally optimal solution? A commonly used approach to get around the suboptimal solutions in non-convex problem is to start the solver many times with a different initial points, and these points can be selected randomly. This process can take a very long time to find a good starting point. Another approach is convexification. So we can convexify the nonlinear power flow equations in the balance. Then the problem is not non-convex anymore. There have been a lot of theoretical results for the convexification method. But even in the radial network, if we needed to consider the lower or upper bounds on the active or reactive power, the convexification method can still have difficulties in recovering the optimal solutions. And now I'm going to still use the two-bus network as an example to show some intuition about how we come up with our proposed algorithm. So we can recall the two-bus network example in the previous slide. There are two solutions, and we call the globally optimal solution theta star and the local solution theta bar. So here I used these two intervals to mark the attraction region of some solution. So the attraction region of some solution means if we start the solver from anywhere within this attraction region, this solver will terminate at this solution. It's kind of like it's attracted by this solution. So the red interval is the attraction region of the global solution, and the blue interval is the attraction region of the local solution. And if the solver reaches the local solution, it will be if the solver reaches somewhere within this attraction region, it will be attracted to this local solution. And if we are using the randomized approach, because we don't know if this is optimal or not, so we may ignore this solution and keep choosing other different initial points. But instead of just ignoring this solution, we may want to ask, is there any useful information we can get from this solution, which may be suboptimal, even if it is suboptimal? And the answer is yes. We can look at the do variable that corresponds to the balance constant associated with this local solution. And with this, suppose let's call the do variable associated with this local solution mu bar. And now we can write out the partial Lagrangian using this do variable. And this is an unconstant problem, so we can similarly we can plot its function values. And the blue line is the function value of this partial Lagrangian. And at the local solution of ACOPF theta bar, we can say the partial Lagrangian has a maximum instead of a minimum. So if we are going to minimize this partial Lagrangian, we can get the minimizer that is within the attraction region of the global solution. So this gives us an idea. What if we start the solver from the minimizer of the partial Lagrangian? Then we will be attracted to this global solution instead of just terminate the solution at theta bar. So this gives us the Lagrangian-based algorithm. We start from the do variables associated with the balance constant, which may be associated with some suboptimal solution. And then we use this do variable to form the partial Lagrangian. And by minimizing this partial Lagrangian, we get its minimizer, and we use its minimizer as a new warm start. And then to call the nonlinear programming solver. And it turns out in this way, we can get a solution with a lower cost. The process can be repeated so we can improve the solution quality iteratively. So in the previous slide, I have shown the intuition by plotting the function values. We say that starting from the minimizer of the partial Lagrangian can get the solver to find the global solution. So next, I'm going to show some geometric properties of the partial Lagrangian, especially the Hessian matrix, the definiteness of its Hessian matrix, and to give more intuition about our proposed algorithm. And I'll use a 3-bus mesh network as an example this time. And still we fix the voltage magnitudes and ignore the reactive power. So we can write out its ACOPF problem. And for this example, we can find 4 solutions using grid search. The first solution is the globally optimal solution, and the other 3 solutions are local solutions. If we check the definiteness of the Hessian matrix, we can say this Hessian matrix is only the Hessian matrix of the partial Lagrangian. This Hessian matrix is always positive definite at the global solution, but it can be indefinite or negative definite at local solutions. And to illustrate this point more clearly, we can plot the contour of this partial Lagrangian, and we'll say starting because of the property of this Hessian matrix, if we start from the start a solver from the minimizer of the partial Lagrangian, we can escape from the local solutions. So let's start from the global solution first. Suppose we start both the nonlinear programming solver and our proposed algorithm from the global solution. And for the nonlinear programming solver, it's actually minimizing a kind of the penalized problem. So if we plot the contour of the penalized problem, it's shaped like a valley, and the global solution theta star is located at the bottom of this valley. So start at theta star, the solver will terminate at theta star. And for the proposed algorithm, we are using the minimizer of the partial Lagrangian as an initial point. And in this example, this minimizer is the right triangle point. It's actually within the attraction region of the global solution. So if we start the solver from this right triangle point, the solver will terminate at the global solution. So in this case, both algorithms can get to the global solution. And now let's start from the local solution, where the hash matrix of the partial Lagrangian is indefinite. For the penalized problem, the contour is still a valley, so the solver will be trapped at the bottom of this valley, which is a local solution. And if we look at the proposed algorithm, because we are using the minimizer as an initial point, and to minimize this partial Lagrangian, we found because the hash matrix of partial Lagrangian is indefinite at the local solution, so the minimizing will not terminate at the theta bar because there's distant direction. So it turns out the minimizer of the partial Lagrangian can be somewhere around here. So it can't be this local solution. So this gives us a chance to get around this local solution. Actually, in simulation, we found the proposed algorithm can always escape from this local solution. This is also true for the local solution where the hash matrix of the partial Lagrangian is negative definite. When we minimize the partial Lagrangian, it has a distant direction to go. So the new warm start will not be the local solution. And the start from the new warm start, the solver can get around the suboptimal solution. So if we formalize the previous observation, we can get the following statement. Let's suppose we start the nonlinear programming solver from some random initial point, and it gets stuck at some suboptimal solution. Then we start our proposed algorithm from the same initial point. It turns out the proposed algorithm the solver in this case can escape from that suboptimal solution. And next, I'm going to prove this statement for n-bus radio networks by using induction. And also, I'm going to prove, I'm going to assume the voltage magnitudes is fixed. And for the case where we optimize both V and the phase angles, I'll talk about that case later. So as a first step of the induction, we have shown that the statement is true in a 2-bus network. So let's look at the 3-bus radio network now. There are 2 types of topology for 3-bus radio network. And it's not very hard to say the second topology is equivalent to 2-bus networks. So I'm going to show the proof just for the first type. And we know SLPF is to minimize the total generation cost. And for this example, it's also equivalent to minimizing the total power transfer loss. So we can rewrite the original SLPF problem as this form. And this form can be further decomposed into 2 sample problems. So to see this more clearly, we can look at the bus 2, 3 first. So given any theta 2, 3 is the angle difference between bus 2 and bus 3. So given any value of the theta 2, 3, we can always find the sum value for theta 1, 2 to satisfy the first balance constant. So it's kind of like there's an implicit relationship between theta 1, 2 and the theta 2, 3. So similar to elimination, we can only optimize theta 2, 3 at first. Then we can have 2 sample problems. In the first sample problem, we only optimize theta 2, 3, and also we redefine the cost function as C tilde to consider the effect of the theta 2, 3 on the line 1, 2. And in the second sample problem, So given the value of Z3, we optimize the angle difference between bus 1 and bus 2. And these two sample problems are just the SOPF formulation in a 2-bus network. So now we reduce the SOPF formulation in 3-bus radio network to 2-bus network, to the case in 2-bus network. So similarly, we can reduce the SOPF formulation in N-bus radio networks to the case of N-1 bus radio network. And if we suppose this statement is true for the N-1 bus radio network, and using induction, we can show this statement is also true for the N-bus radio networks. For the case where we optimize both the voltage magnitudes and the phase angles, we can have the following statement. Let's call the global solution of SOPF X star and the local solution X bar. And the mu bar is the Lagrange multiplier associated with the balance constant at this local solution. Then we can form the partial Lagrangian of this SOPF using this Lagrange multiplier mu bar, and we have the following result for the hash matrix of this partial Lagrangian. This hash matrix is a positive definite at the global solution and the negative definite or indefinite at the local solution. So if we use the minimizer of the partial Lagrangian as a warm start, we won't have the issue of getting stuck at some local solution. Instead, we can escape from the local solution. And we have seen that the statement is true in a 3-bus mesh network, but the formal proof for larger networks can be much harder. So, but we test our proposed algorithm on different sizes of IEEE standard networks, and the simulation results show that our proposed algorithm can always find the global solution within 3 iterations. So next, I'm going to show some simulation results of our proposed algorithm. We have tested our algorithm on different sizes of the IEEE standard networks, but I'll show the simulation results in a 39-bus mesh network first. And in this example, we can find 2 solutions, and we start the solver from 600 different initial points, which are selected randomly. And after direct call to the nonlinear programming solver, without performing our proposed algorithm, there are only 47% of all these 600 initial points can lead to the global solution. And the average cost is as high as 30% higher, is 30% higher than the optimal cost. And after performing a single iteration of our proposed algorithm, we can make 98% of all the 600 samples to get a global solution, and the average cost is decreased to 1.5% higher than the optimal solution. And after 3 iterations of our proposed algorithm, we can make all these 600 samples to get a global solution. For the 118-bus mesh network, there are also 2 solutions, and our proposed algorithm only need 1 iteration to find the global solution. And in this figure, I choose a subset of buses to show the solution of the phase angles. The blue line is the local solution, and the red line is a global solution. The yellow line is the solution of the partial Lagrangian. If we use the solution of the partial Lagrangian as a warm start, we'll find the global solution instead of getting stuck at local solutions, because the local solutions are very far from our initial point. We can have similar results in the 300-bus mesh network and the 141-bus radio networks. So to sum up, we propose a Lagrangian-based algorithm that can improve the solution quality of ACOPF iteratively. We have tested our algorithm on different sizes of the IEEE standard networks. It turns out no matter where we start our algorithm from, our algorithm can always find the global solution within 3 iterations. That's all I'd like to talk about. Thanks for attending this lecture. And if you have any questions, please feel free to contact me at this email. Thank you.